Hello, good afternoon. My name is Philip Taylor. I'm Hydro International Stormwater Product Specialist for America's Stormwater. I'll be giving this presentation. We have approximately 350 people registered for this presentation, so I'm really pleased with that. That's an excellent registration rate. It's always pleasing to have a lot of people register for these webinars. That tells us that they're on point and people enjoy them. So if I can get this advancing and working, here we go. Just a few housekeeping things before we get started. We do have a post-webinar survey. This is part of our system. It really helps us with developing future webinars and getting feedback on the quality of the webinars. Please stick around and take that post-webinar survey. It will start automatically on exit from the webinar. PDH certificates, those will be emailed out automatically tomorrow, as well as the winner of the $50 Amazon gift card, which you can win by doing that post-webinar survey. That'll be winners will be notified tomorrow as well. As I said, we have about 350 people registered. Currently online, we're probably looking at about 160, 170 people, so that's a really good turnout. The presentation is being recorded and will be available through Hydro's YouTube channel, as well as I put them onto the GoToWebinar page for Hydro International. You might be able to find that, but in addition, I PDF these presentations and upload them. So if you go to the handout section of the control panel that you're looking at, you should be able to download the PDF copy of this presentation for your own reference. A little bit about Hydro as an overview. I'm going to look at the history of sewers a little bit. I find it useful when doing these webinars and you're given a topic to talk about that you're not too sure about. Look back in history tells you a lot, and so I've actually learned a lot by doing this webinar and preparing for it, and I wanted to share some of that. Then we're going to look at the green infrastructure and the LID, or the low impact design side of things, and the working of low impact design and grey infrastructure together, and then look at what may be the future steps in stormwater management. As always, we like to start and tell people a little bit about the company that I work for. Our specialty is stormwater treatment, or water treatment in general. We do stormwater, wastewater, and combined sewers. The technology between stormwater, wastewater, combined sewers is actually very similar these days. Over 30 years, probably close to 40 years of structural BMP treatment of stormwater. And we have thousands of separators, filters installed around the world. And we have a world-class hydraulics lab, which I'm going to show a few pictures about, show you a few pictures of in a moment. Just to give you some idea of how far back Hydro International goes within this industry. Bernard Smisson was one of the founding fathers of the company. He was an inventor and an innovator. He was a city engineer for the city of Bristol in the UK. He developed a lot of the early research into swirl concentrators and vortex flow control devices. He worked with the American Public Works Association on developing swirl concentrators for combined sewer overflows. There's a number of papers I found in preparing for this that have been scanned and are available on the internet referencing Bernard Smithson's work. And in 1974, he was recognized for his work by the American Public Works Association with the Award of Merit for his contribution to the development of this technology. And as a timeline for Hydro International, from the early 60s, some noticeable milestones. In 1986, Hydro set up an office in the US, based in Portland, Maine. 2005, they built a hydraulics lab there to do testing of stormwater and wastewater products. And jumping forward a few years, 2008, we acquired UTEC Systems, a CSO pre-screening systems out on the west coast of the US, and that became our combined sewer office and location. In 2016, Hydro acquired HydroLogic, which is a monitoring and instrumentation company in Europe, which really took us on the path down to sort of the future of stormwater management with the use of monitoring systems and instrumentation of stormwater and wastewater. This year, we have actually significantly invested in the labs, and I'm going to show you a few pictures of that, and acquired M&N electrical and mechanical service in Europe to further enhance our maintenance side. We actually also do maintenance of stormwater and wastewater products as well. And the maintenance division is a growing area of stormwater and wastewater management. So some pictures of the new lab. The guys who wear white coats in our office in Portland, Maine, are very proud of this. Basically, they stripped out the building, completely threw out the old lab and built a brand new, basically a world-class hydraulics lab. It consists of two separate insulated, temperature-controlled reservoirs, which can be split into two apiece, so you can actually have 4 independent reservoirs. It can test full-size 4-foot manhole-based systems, bench scale testing, rapid prototyping. The capacity of this new lab is quite amazing, and we're very proud of it. And this allows us to do a lot of research and development and understanding the technologies that we're working with. As a company, we're spread around the world, over 300 employees now, close to 350 employees. And we do work all around the world. I work in the stormwater department, so my specialties are the swirl separators, the downstream defender, first defense. We have screening systems for gross pollutants. We have vortex flow control valves, upflow filter systems, and bioinfiltration systems. So if you need to know anything more about that, you can either contact me or get on our website and take a look at those. Okay. So when someone says to you, would you like to do a webinar and a presentation on when green meets gray, your mind doesn't immediately jump into a whole lot of stuff you can talk about. It's a little bit like oil and water at times, and certainly when I go to conferences and I sit in on these presentations where the green meets gray and the green versus gray conversation comes up, you can get some pretty heated debates. So I started off by going back and looking into history a little bit and just seeing how old is this green stuff and how old is this gray stuff, and is there any overlap in the past where they've worked together, and what I could find out. And it took me down a bit of a rabbit hole, which our team in Hydro gets together, and we pre-vet these webinars, and they brought me back down to earth a little bit, and I trimmed it up, and this is what I've got to present. So when we look at the history of waste and stormwater, it really is a combined sewer system. There are systems going back, and the earliest constructed stormwater systems were found around 2500 BC or BCE through to about 1000 BC, and Bronze Age basically. These systems were constructed from stone, basically to move waste away and also to capture stormwater and empty them into cisterns for use. But many of the modern septic systems would be instantly recognizable by these ancient systems, or the builders of these ancient systems, because they have many similarities, and of course their purpose is the same thing. It's to move waste away and capture and use rainwater. Now, some of these systems still are in service. The Romans and Greek built extensive sewer systems, brick line and stone line systems. And this picture here is one that's still in operation today, I believe, in Rome. But somewhere around the end of the Roman Empire, around about 500 AC, sort of thing, the Roman Empire fell apart, and organized cities on a large scale kind of fell into disrepair, and the Middle Ages took over. And as they went through the Middle Ages, sanitation and cleanliness became less important. They became less of a focus. So a lot of these systems fell into disrepair, And of course, disease and pestilence followed, and there wasn't a strong connection between sanitation and disease at that point. And moving into the medieval times and to the early modern age, the streets themselves were the sewer systems. And this led to the fashion of capes, men with high-heeled shoes to keep the trousers out of the muck, wide brim hats and stuff. So fashion was influenced by the fact that people were throwing effluent out of the windows of their houses, and you wanted to keep it off your person. And on the right-hand picture here, an early internal plumbing toilet basically just drops straight into the street. So the streets themselves were the system of disposal. And then we moved into the modern age, and the modern age isn't quite what you think. It's around about 1492 through to about 1789. And the first industrial revolution came along. And in London, certainly an area where the industrial revolution took off, storm drains and effluent poured straight into the Thames. And in a period around 1958, 1959, it was a year known as the Great Stink. The effluent had built up so badly in the Thames, and it was a year of unusually warm conditions, that it created such a problem. And I can just imagine living in a time with effluent in the street and the heat in the streets. The smell of the streets and the cities at that time must have been somewhat overpowering. But anyway, the Great Stink created a movement and a development of basically the grey infrastructure, where combined sewers were developed to move the effluent away from the centres of population and to dispose of it downstream. So that became the grey infrastructure. It wasn't until the second industrial revolution, that's the technology revolution, and that's where internal combustion engines became common, power, electricity became more widely used, that the combined sewers became more common in use, and cities designed these in. So when we look at this, the period of 1870 through to 1914, which is pre-World War I, that's really, in terms of history, not that long ago. And so the idea that stormwater and wastewater was a waste product, basically you had to get rid of it and just drop it into the nearest water body, and hopefully it would just float away. Now, a couple of things happened in the mid-20th century. And this had a significant influence on what we do in stormwater today and why we're doing it. In 1954, there was the accelerated depreciation law. Now, prior to 1954, when you built a commercial building or a commercial development, it was deemed to have an age of 40 years, and that you could depreciate your property and your buildings, your assets, by 1/40th every year. So it was a linear depreciation. That meant that if you were developing a mall, you really needed a center of population around you that you could rely on for rental income and use of that property. You couldn't risk a long period of low income. So there was a big concentration on development prior to 1954 of maintaining a main street or a downtown center. That was where the money was to be held. But once you got past 1954, there was a mild recession. Congress passed what they call the accelerated depreciation laws. This allowed developers to compress the depreciation of a property into the first few years of its life. Now, that transformed their ability to develop greenfields, because now the risk of loss was greatly reduced. They could claim back a lot of money very quickly on a property that technically could have no tenants. So they could go out and develop greenfields. So we had this massive expansion of greenfield development on the city fringe. So that was a major changing point in basically the development of impervious surfaces. Remember, at the same time, this was post-World War II now, you had a very wealthy population, a lot of stimulus money coming back, a lot of people coming back from war. The government was building interstate highways. They were helping people buy houses through the production, I think, Fannie Mae and Freddie Mac. So there was a tremendous push to develop land, and people could move freely on the interstate freeways to towns that were previously isolated from main centers and develop what they called ex-urban developments, where you could develop land in a small town and commute to the city. So there was another thing that happened in the mid-20th century that had another tremendous impact on impervious surface. That was the Real Estate Investment Trust Law, or the REITS, in 1960. Now, it's known as the Amendment to the Cigar Excise Tax Extension of 1960. That happened to be the first thing on the list. It was a group of laws that were put together. That was the first one on the list and was signed in 1960, and it became known as that Cigar Excise Tax Extension. But really, within that, there was a page for REITs. REITs allowed investors and corporations to group together and invest in income-producing property. And they could do it with pre-tax money. They could then get back 90% of the money from the rental income and offset that with the depreciation laws. Effectively, it created a tax shelter through rental income. This just made developing greenfields even more attractive. And an example here, this is a 1.1 million square foot multi-tenant industrial REIT. So you can see, just looking at this, the massive increase in impervious area. And when you look at this, you don't see a lot of stormwater BMPs around it. It was purely about maximizing the value of the property. So we have all this coming together and creating basically a situation where you're really incentivizing development, and at the same time, industrial farming was coming along. Industrial farming reduced the need for farm workers. And now we have a shift from the country to the urban living situation. And if you look at this chart, 1940, 1950, things started to really take off in the urban shift. So we have more people living within an urban environment, less people living in an isolated, smaller rural environment. That put a lot of pressure on existing infrastructure. So all those combined sewers, which are starting to be built around the late 1800s, early 1900s, were now having to work with a lot more people. Now this created the combined sewer overflow problem we have even today. Massive increases in impervious surface, increased urban population, shorter runoff times, greater runoff volumes, concentrated pollutant loads, and you get these combined sewer overflows. As you can probably guess, combined sewers overflowing into rivers and streams did a lot of damage. The environmental movement came along. That started somewhere around about 1956. People started to become very aware of the damage that was being done. And 1972, the Clean Water Act came into being. And following that, as part of the Clean Water Act in 1994, we had the CSO control policy, which was basically written to stop these combined sewers overflowing and polluting the environment. Now, prior to all this, mechanical screening was the main form of treatment, settling out a bit of sludge and then disposing into a waterway. That was the basic wastewater treatment system, combined with the combined sewer and the stormwater in the same pipe. The CSO, the overflow, was quite common. So April 1994, US EPA issued the CSO control policy mandating that communities dramatically reduce or eliminate these overflows. You've only got one pipe, right? 1994 and the early 90s was a significant year because a lot of things started coming together. A lot of pressure on cities now to separate out the stormwater and the sewer pipes. Now here's a fun fact with all this. 1.1% impervious problem, I called it. If you look at the United States, the pavement and impervious surfaces cover around about 43,000 square miles in total. That's about the area size of Ohio. About 65% of that is purely dedicated to cars, streets, parking lots, and driveways, basically transportation. So 1.1% imperviousness for the United States, and we got all these problems. Now, it's not evenly distributed. It's concentrated around water bodies, rivers, lakes, and oceans. These were the primary transportation systems of the old times, and so that's where the development took place. So we have high density imperviousness in these very sensitive areas. But it does make you think that, you know, if we can do all this damage with just 1.1% impervious on a sort of a global scale, we don't want to go too much further. We really want to be backing out of that imperviousness. Of course, with the CSO control policy, the immediate thought, engineers went, okay, we need more pipes. So, you know, we add more pipes. That solves the CSO problem, but it also highlighted another problem. Turns out, you know, when you start separating stormwater and trying to get rid of it, there's a lot of it, and turns out it's pretty polluted. And there wasn't a big focus really on water quality at that stage, in the early stages. And I remember my training in the mid-80s. I was working for a water and soil conservation district, and we were doing lots of water quality testing and water and soil related work. And I moved to a local county where I became a county engineer working within the engineering team. And we developed wastewater treatment systems, which basically consisted of a screen in a pond, some primary settling, some UV stuff from the sky, and disposed into the local waterway, maybe a long pipe out into the ocean a little bit to get it far enough offshore. And when it came to designing a stormwater system, it was just about catch basins, pipes, down to the local river or lake, some rock scour prevention, and that was it. You know, the water quality component wasn't even in the manuals. So now we have, you know, stormwater separated from combined sewers, and turns out it contains solids, it contains trash, it contains nutrients. There are temperature problems, there's turbidity problems, you got volume and scour and flooding, you've got metals, and you've got hydrocarbons. All in all, this stuff's pretty dirty. So we have to deal with that. So this is where we start to get to where green, gray, low impact designs start to come together a little bit, because we all start to think about this and go, you know, this doesn't seem to be working one way, maybe we can try another. And what we had was the low impact design concept. Now, there's some important confusion going on around here, I think. When we look at low impact design, it operates at a site scale. So it's individual practices developed for a site. The low impact development or design term was coined by Larry Kaufman and his colleagues in Prince George's County, Maryland, in the early 1990s. In 1998, Larry Kaufman helped found the Low Impact Development Center that now uses this definition. Low impact development is a comprehensive land planning and engineering design approach with the goal of maintaining and enhancing the pre-development hydraulic regime of urban and developed watersheds. So it's a hydrological model, basically. Within that, obviously you can do water quality components as well, but the primary approach of low impact design or development is to mimic your pre-development conditions and sometimes even pre-settlement conditions. So that's a challenge in itself, to do this mimicking. when you're paving over all the area and you're trying to concentrate that the filtering, the infiltration, the storage, evaporation, and reuse of rainwater into a small footprint. You're asking a lot from probably the native soils, and you have to do some engineering and modification of the soils. Now, green infrastructure is often used in the same context, but when I looked into it, turns out that green infrastructure actually was something different. Green infrastructure operates on a landscape scale, and it's about reconnecting disconnected areas of green space for environmental purposes like migrating animals and for species diversification, and basically for safety as well. You know, I live here in Wisconsin, and I drive 6 miles some nights out to the barn where we keep a horse, and at night, especially in the fall, they're a real problem because they're crossing the roads. When you put an interstate highway between two green spaces and you cut off that connected system between these two green spaces, you end up with a lot of insurance claims and dead deer. So green infrastructure recognizes the value of reconnecting these green spaces to protect the environment, to protect people, and it adds a tremendous amount of value to the environment. So the term green infrastructure turned up about the same time, about 1994. And unfortunately, the term in 2007 was somewhat confused when the US EPA began to use it to refer to BMPs that were actually low impact development strategies. So we have this mix of terms. And I think the word green has confused things a little bit. If you think green, you start thinking immediately that it has to be plants, or it has to have something like that in it to make it work. Whereas if you think low impact development and hydrology, you can separate from the green and go, I can design something that's low impact, mimics hydrology, and may not necessarily be green. So there's a middle ground in there somewhere. So when we look at green and grey infrastructure, there is room to put both these together. For instance, you're seeing a range of photos here incorporating both green and grey infrastructure, but the purpose of these things is the same thing. It's to treat pollutants and to really just mimic hydrology. Now, like all things, when it's first new, and when we think of green infrastructure or low impact development, it doesn't have 3,000 years of steady history, perhaps like the grey infrastructure has, even though in early times, rain collection and management of rainwater was important to ancient people. But when we look at more recently, that the LID, the low impact design, really came into play around the early 90s through the mid 90s and early 2000s. And there was a lot to learn. Some of the things that really caught people out was, you could design it, implement it, but not really understanding the infiltration rate of the underlying soils and having failures on infiltration. One of the big things was contractors, when faced with these things, actually didn't know what they were building, the importance of staying off them, over compaction, improperly building them. This is none of their fault. This is all new stuff, so people are learning. And there are two areas here really that are still being really investigated and we're learning a lot about, and that's the understanding of maintenance and pre-treatment. Not designing for proper ease of maintenance. And the other thing is owners. It's very easy to design something within the low impact development way and grey infrastructure actually now, and you design it, someone builds it, the property's sold, the new owner has no idea what they have, and in the case of a rain garden, immediately calls in a contractor to mow that messy thing down, and it disappears. And the inventory tracking systems weren't in place to go back and say, hey, you can't do that. That was an important system to manage the stormwater. And then the O&M infrastructure was missing. With traditional grey infrastructure, manhole pops its lid, floods, you call the city, someone comes out with a Vector truck, they pump it out, they've got the right equipment. But if your rain garden failed and it flooded and you called the city and they send out a Vector truck, the guys would stand there and go, I have no idea what to do with this. So it was completely different infrastructure was needed. So all these things are falling into place now. But some of the learning things that we see, and I was at the, it was the Stormwater Maintenance BMP workshops in Minnesota about 3 weeks ago. And if any of you went to that, it was a tremendously useful and informative workshop, 3-day workshop. The quality of the presentations was very good, and a lot of learning basically around low impact development and individual BMPs. And there were a couple of takeaways that really came out of that from many people was, A, was designing for maintenance, and B, was doing the maintenance. It turns out a lot of these systems are actually quite robust, that they will last for quite a long time, many decades, and some of them now are just getting to the point where they're coming up to their sort of life cycle endpoints. They're 20, 25 years old. They're not that old in terms of history. But we're finding that these systems that, even though they might be slightly neglected and they have maybe some invasive species in them, even at 20 years old, they're still working pretty well, providing a certain minimum maintenance was done on the pre-treatment side to protect the system from being overloaded by gross solids and certain types of pollutants. So here we have a picture. This is Melbourne in Australia. It's a warm environment. Leaf litter coming down the street, going into the BMP here. But when you think about this, you've got a nice stone garden, obviously you've got storage and infiltration going on under here. How are you going to get that leaf out of there? Because at some point that's going to break down into a matter of organic material on the surface. And it's not easy to get that out. So the thought about how do we maintain that? And this is an example perhaps of a cold climate situation, and I see this a lot around where I live. I can walk around and look at these rain gardens or these bioinfiltration systems and see that the inlets have filled up with winter grit, or even a deteriorating street situation when you're losing the surface texture of the street. And you get a lot of this gross pollutant stuff, pebbles and sand in the inlet that builds up. And clearly it hasn't been maintained for a while. It's growing here. And that forces the unit to go into bypass, and water just bypasses completely. The water's not, you can see in the top left there is a bypass structure designed to take the high water, but the water can't get into there. So this is part of the learning about doing these rain gardens. And what we're finding is that, yeah, they're great systems. They do what they're supposed to do, but there has to be a bit of focus on the trash, the gross solids, and the hydrocarbon side to allow. And you can see in this photo here that I got, someone's doing some work here, but they've actually put, for some reason, some sandbags on the inlet to do some work here. So if we just look at this, things that grey infrastructure do really well turn out to actually complement the things that green infrastructure doesn't do so well. And the things that grey infrastructure does badly, turns out green infrastructure can do very well. So if we combine the two, we can actually do pretty well. And here's an example. This is something that grey infrastructure does really well. It removes trash and gross debris. These are the downstream Defender pictures that we took inside some of our water treatment units. And this is stormwater, and you can see how dirty it can be, how you get a lot of pollutants in there. And if this was going into your rain garden, it's kind of a visual mess. So it can be collected below grade, out of sight, and then pumped out with a Vector truck. That makes the whole place look a little tidier, because one of the big benefits of a low impact development is its visual appeal and the value that adds to a site, to a property, or to a street. And that's something that should be encouraged, but we need to address the gross pollutants. because your LID systems really, especially when it comes to maintenance and basically infiltration, you want relatively clean water, and you have to pre-treat that water. And some examples of learning, and these examples are actually presented by owners of LIDs within the BMP workshops conference that I went to, as things that they learned that they didn't really think about too much. But they've gone back and actually retrofitted a lot of these systems with better systems. One thing you need to deal with water coming off the street in your curb cuts is the velocity of the water coming in and stopping erosion and scour. And the logical thing to do with that is just use a pebble or rock inlet. Unfortunately, that doesn't think too much about how do we clean or maintain this. And one of the stories related was that they sent out the Vector guys to do some maintenance on a curb cut inlet, and the instruction was scrape it clean and remove the debris and gross solids. And of course, the first thing they turn around and look at the Vector truck and say, what with? I've got a Vector truck. And so they started to develop tools to do this. But if you've ever tried to remove stones that are embedded in soil, this is a slow and time-consuming process that really doesn't encourage success. If you have to do this and in some cities, they may have thousands of these rain gardens, this isn't a recipe for success. So what we found is that when you start looking around, people have recognized this and gone, we really need to do something slightly different so that we can use more efficient infrastructure or more efficient tools to do the maintenance. And you can see in this photo, this looks to me like a bit of a retrofit that someone's gone, hey, we've got a bit of a problem here. What if we put some gray infrastructure around this? Literally put some concrete in here, act as a buffer. Now we can either use a shovel or we can use a Vector truck to clean this out. And so you have an early development saying, okay, now we're thinking about maintenance and pre-treatment. And then someone goes, I can actually do that better, because that other system, you have to go back and do it every month. What if I put a sump in here and now I've got a manhole again, we're going back to gray with a sump, put a grate on top of it. My pre-treatment system now can go 6 months or even a year before I have to come back and clean it. Now that's much more efficient. It also means that your rain garden is working better. It's not getting that pollutant load. You have a way of doing that. And then downstream, you can see that second inlet there, that curb cut, that could actually be a hydrodynamic separator to treat the bypass water. So you can separate and actually do a more efficient job overall. So now we're seeing basically the combination of green and gray being used together. Now we have a few things to address. What I see in many stormwater manuals, there was a tremendous shift from gray to encouraging green infrastructure or low impact development, to the exclusion of gray infrastructure, basically. In many manuals, I see words or intent that if it's underground, you can't use it. Or if it's underground, you have to say every reason why you can't use an above ground system first, which for many sites makes the engineer work really hard just to get their stormwater compliance. And that if the manuals were a little more flexible to allow the green and the gray to work together, it would be a lot easier. But yeah, this all takes time. Data collection is an important thing. We're developing knowledge, we're developing understanding now. The thing we have to recognize is that this is not old, we're still learning on how to work these things together. And with that, I'm going to sort of introduce some more of the concepts to move forward. This is a rendering we had done for our own promotional work a few years ago, where the pre-treatment system is incorporated within the low impact development, so that you have maintenance at a place where it can be maintained and can be maintained with efficient equipment. I always sort of get a smile when I look at this rendering, because I noticed that the artists must have looked at a few pictures when they did the rendering and immediately put an invasive species into the pond rather than putting in some nice native plants. So when we look at this picture here, we can see the marriage of what might be deemed grey infrastructure and green infrastructure, especially in a retrofit situation or a situation where you know, the cost of a development is offset by the amount of usable parking spaces required under the law to provide, that you can use the grey infrastructure. What you'd look at and think maybe that isn't green, but it might be low impact. That could actually be an infiltration system, which would make it low impact development. A pre-treatment system, a flow control system, and then a system of infiltration, or maybe even further remediation through total phosphorus removal or some other treatment system within this natural processes of the soil. Now, I did find a really interesting document when I was doing research for this, and I highly recommend everyone look at it, done by the University of Arkansas, the Community Design Center. There's a link at the bottom of this slide that you can use to find this, but it's a tremendous document of low impact development. And in some of the renderings like this one, it's pretty idealized. You realize that if you're in a cold climate, you're not going to park way over to the right here and walk to the front door, because you know, you'll freeze, slip, or whatever before you get to the front door. That most of the parking would be here, that you might have more intensive impervious surface here and more broad general treatment out here. But these sort of concepts have to be balanced with the practicality of treatment, maintenance, cold climate conditions, hot climate conditions, and everything else that goes with that. And while I was doing this, I was actually digging back into some of the old presentations we had done, and I went back about 10 years, and somewhere around 2005, 2000, in fact, that's more than 10 years, 2008, I found this rendering in one of our old presentations where we had looked at this treatment train or combined treatment system. We have the pre-treatment system, a flow control valve to balance it out to a storage system so that water would come through pre-treated in the early part of the storm, go straight to a treatment system. Now, this could be either filtration, infiltration, it could be bioinfiltration, could be a range of systems. And then when the flow grew too large for this to handle, it would force storage, come back in as the storm passed, and then go through treatment again. And this could go back into an infiltration system or a water reuse system. So Hydro was looking at this quite a number of years ago, but because when you draw something like this, people immediately see, oh, it's grey infrastructure, it doesn't fit the green word. But if you looked at this as low impact development, it would actually fit very well. So let's introduce the future, what I believe to be a tremendously powerful tool coming down the pipeline, and that's instrumentation. Now, this is part of the investment of Hydro into hydrologics, and it was recently that I was shown an example of this that I realized the power of this in terms of stormwater management. So if I take an example, here we have an upflow filter and some dimensions here. From the sump to the bottom of the filter media is about 24 inches. The filter media itself, about 9 inches high. And then the operating head, the pressure that goes on that system is about another 20 inches. So you need that driving head to make it work. So this comes together as the dimensional physical layout of an upflow filter. And you put these into the field and you button the lid up and you hope they work. By adding in instrumentation, we did this for an industrial job to help analyze some questions around the effluent measurements we were getting. So here on the left, we have the actual inches of measurement up the side of the unit, and we have simply a water level measurement tool within the system. And you can see here, no water, it was cleaned out, sump was emptied, the instrumentation put in, and it's reporting 0. And then it starts to rain, fills up. And this top of the green level here is that top of the bypass. That's the maximum operating head that we want it to run at. And it comes down. And this is the static water level. This is the outlet pipe level. And then another rainstorm event. And we can see a really nice pattern of operation here. This piece of equipment is working exactly how it should be. It's not bypassing water, and it's draining down to the correct level after the storm passes through. And this carries on for some time. Maintenance was carried out, the sump was drained, the sensor showed the sump was empty, and then it started to rain, and normal operation continued. Period of very little rain. And then we had some larger storms, and we get bypass water, so we know how much water is going through the bypass. But afterwards, again, the system drains back down to its normal static level. We see no problems with the operation. Until this point, then we see a period here where the water isn't returning to its normal level, and an alarm goes off in our system saying, hey, here's a system that now needs maintenance. The drain down system, which controls this last piece of the water level drop down to where it should be at the static water level, clearly has got something blocking it, and we can go out and do some simple maintenance and restore that system back to operational condition very quickly. And that's the power of just a simple water level sensor, remote sensor, hooked up to the internet that can be viewed from anywhere in the world. This is the sort of thing coming down the line where we can actually match grey infrastructure and green infrastructure together. Because imagine if this was a sensor sitting over a rain garden or a bioinfiltration system that's measuring the water level in that. You would immediately know or see the performance of that system over time and know that from your office whether the soils are infiltrating as they should be, whether the system is draining down within the time it should be, or it's draining too quickly. Currently, you'd have to go out and do an infiltration test, and you know, so this is a very powerful tool coming down the pipeline for the future of stormwater and stormwater treatment. And this is where grey and green, I think, are really going to come together. People are going to see the value of putting these two systems together, putting the green infrastructure, the low impact development, and instrumentation all together to produce a much smarter system that allows you then to target your maintenance, put the money where it needs to be, and not spend money where it doesn't need to be. The savings and that sort of thing would be tremendous. Instead of just running around every year cleaning every catch basin, you might be able to monitor water levels and pipe systems and say we need to clean this area, but that area is doing okay. So that's just one example of basically the new technology coming down the line. We have e-guides on that you can get from our website. So I hope I've entertained you, given you some information that might be useful, made you think a little bit. There was no great teaching as such in terms of, hey, here's how to make green and grey be the same thing. I think they need to work in partnership. Remember to do our post-webinar survey, going into win for a $50 Amazon gift voucher, and PDHs will be sent out automatically tomorrow. If you don't see them, or if you have more than one person in the room and you want additional PDH certificates, just email us. We will arrange to get that out to you. My email address is there. So with that, I would like to thank you very much for your attendance. I hope I haven't bored you too badly and that you've got something out of this. Thank you very much.